So welcome back. We're discussing Diels-Alder reactions, and we discussed basic Diels-Alder reactions, and now we're going to discuss the difference between endo and exo preference. Before we get to that, let me remind you, the other day we talked about the difference between the S-cis and the S-trans conformations of butadiene. So we can rotate about this single bond here and achieve S-trans or S-cis conformations at room temperature. At room temperature, we're going to primarily have the S-trans conformation, and we'll have a small proportion of molecules that are in the S-cis conformation. We need the S-cis conformation in order to perform a Diels-Alder reaction, but as long as the molecule can achieve an S-cis conformation, we can usually get a good yield. But if we can actually lock a molecule into that S-cis conformation through, say, a cyclic system where we have a bridge here, then the molecule will react much faster. If that's not a possibility, such as in a situation like this, if we can't achieve that S-cis conformation, then we're not going to get a reaction at all. So you can see here that we get no reaction. But molecules that are locked into that S-cis conformation, such as cyclopentadiene itself, will actually achieve a much faster reaction. In fact, cyclopentadiene is so reactive toward the Diels-Alder that it actually reacts with itself in situ and undergoes a Diels-Alder reaction in order to form a or in this case, tricyclic system. And so you saw in the lab that you had to actually crack these two monomers apart because we had the dimer, the dicyclopentadiene dimer, and you had to crack them apart in a retro Diels-Alder in order to get cyclopentadiene in order to do your reaction. Okay, so we did a reaction similar to this, but we used maleic anhydride in order to get a Diels-Alder reaction for lab. So let's see if we can draw the product of this reaction. So this is very similar. Our carbons would be labeled in a similar way to what we saw the other day. Carbons 1, 2, 3, 4, 5, and 6. Okay, and so we can draw a 6-membered ring that we would get for our product. And this would be carbons 1, 2, 3, 4, 5, and 6. Now we've got this little 1 carbon left over here, and that's going to give us our little 1 carbon bridge. Okay, so if we draw the mechanism, we're going to get a product between 1 and 6, and between 4 and 5. This pi bond becomes a sigma bond, this pi bond moves, this pi bond becomes a sigma bond. So we end up with a pi bond here, and we end up with our aldehyde groups, and since they're cis in the starting material on the double bond, we're going to get they're going to be cis in the ring that forms. Okay. So the interesting thing about forming these bicyclic systems like this is that we can have either an endo or exo preference. Okay. So here we have a 1 carbon bridge, and we're going to refer to these as endo or exo to the larger bridge where we have this 2 carbon bridge here. So if a substituent ends up on the bottom, it's going to be endo to the larger bridge or syn to the larger bridge. If it's exo, it's going to be anti to the larger bridge or exo to the larger bridge. We're going to see that endo preference is actually, endo is actually preferred, even though it might seem that exo has less steric hindrance. And that is because when this reaction is performed with the endo isomer, we have overlapping molecular orbitals, which has a favorable interaction in the developing bonds that are formed. Okay, and so endo is the preferred isomer. So what are we going to have here? If we draw this product, we're going to have both possibilities, endo and exo. Okay, and so we're going to see that endo is actually the preferred isomer. So let's see if we can work some problems with that. Okay, so this is 17.19, and here's A. Okay, so first I'm going to draw it in a similar way to what we had before. We're going to form a bond between carbons 1 and 6 and carbons 4 and 5. So this pi bond becomes a sigma bond. This pi bond moves to the back. This pi bond becomes a sigma bond. So we can draw that just like the previous products. Okay, we have a pi bond in the back, carbons 1, 2, 3, 4, 5, and 6. And we have our cyano groups that are going to be cis to each other on the ring. Okay, so we formed this sigma bond here and this sigma bond here. But we also have this one carbon atom here that's going to form a one carbon bridge. So if we actually drew that in our regular bicyclic notation, what would it look like? It would look like this. Okay. And in this case, our cyano groups, we drew them up. Okay. And that is the exo isomer, but we also have the endo isomer possible. Okay, where our cyano groups are down. They're going to be cis to each other either way, but here we have the endo isomer that's possible, and this is endo to the larger 2-carbon bridge. Okay, so this is going to be our major product due to the favorable overlap of the orbitals during the formation of the product. So I'm going to work like one more of those, I think. This is D from that problem set. Okay, so again, 1, 2, 3, 4, 5, and 6. I'm going to draw the product in the traditional way. One, 2, 3, 4, 5, and 6. Our double bond is in the back. And here we have trans substituents. So what does that mean? So I forgot our little sulfur bridge here. So what does that mean? If we turn it over, we're going to have this bicyclic system, and one of those is going to be up and the other one is going to be down. Okay? That's because they're trans to each other. So we don't have endo and exo preference here. We just have the possibility for enantiomers where this carboxylic acid group could be mirrored in the enantiomer, and this one would be mirrored going down in the enantiomer. All right, so let's do just one more of those. Let's do F. Here we have maleic anhydride. Okay, so how are we going to draw our product? 1, 2, 3, 4, 5, and 6. Okay, we're forming a bond between carbons 1 and 6 and 4 and 5. And let's go ahead and draw with red. 1, 2, 3, 4, 5, 6. All right, so what do we have? We have a double bond in the back, and now we have that ring. The other 3 atoms that are in the ring, okay, can either be coming out at us, okay, or they can be going away from us. Forgot our little oxygen bridge here. All right, so what is that going to look like? It's going to look like this. Okay, it's going to look like this, where they could either be, where the ring could either be up, and that would be exo, or we're also going to see this isomer formed where the ring is down, and that's going to be endo. Okay, so our hydrogens are up. So if you draw this on the test, you need to be able to clearly show where these hydrogens are ending up, because that's going to indicate that you understand the endo versus the exo preference, and endo is going to be our major product. Okay. All right, well, we're almost done with Diels-Alder, and in fact, we've covered the information that's in versions 1 and 2 of Klein. But I want to discuss a topic that's included in version 3, which is regiochemistry. So there is regiochemistry possible in a Diels-Alder reaction if we have an unsymmetrical diene and dienophile like this. So here our diene is actually has a methoxy group on it, has a substituent. And our dienophile also has a substituent, and so we see that we can get two different products. We can get these can be added opposite to each other in a 1,4 fashion, or they can be added and closer to each other in a 1,3 fashion. Okay, so which is going to be the more likely product? In order to determine this, we have to actually consider partial charges. So we can draw a resonance structure for this methoxy group where a resonance is observed into this double bond. So we can have a partial positive on the oxygen and a partial negative on that carbon. Remember, that carbon is the one that we're forming a bond with. Our dienophile also has a resonance, and so we can draw a resonance structure where our positive is here on this carbon, negative on the oxygen. So if we put those guys together, we've got negative here, positive here, and when we draw our bonds, we want to line these negative and positive charges up, these partial negative and partial positives. And so here would be carbons 1, 2, 3, 4, 5, and 6. And so we could draw a bond between 1 and 6 and 4 and 5, giving us the product. Okay, and so this 1,4 isomer is going to be our major product, where these groups are opposite each other because of the way these partial charges line up. Now, I'm not going to include this section on your exam, because that section is not included in versions 1 and 2 of the book, and therefore I'm not going to work any problems with it. But if you want to work problems with this problem set, we can certainly do that, and I can do that in class, or I can do that with you one-on-one. All right, and thanks for watching, and have a great day.